Good morning.
Good morning.
How are you?
I'm good. How are you?
Doing very well. So the live stream is up and working. Do you have the link for that?
Yes, I do. I'm gonna
Perfect.
hop on right now.
And yeah, so it's set the meeting controls so that participants can't share screens, but co-hosts can. So the key is as people come on, I'll make those in the core joint initiative co-host themselves. And then there's a security setting that allows participants to unmute themselves that I'll turn off once the first presentations get going, but then we want to turn that back on so participants can unmute to ask questions. And then otherwise, I didn't see any emails about issues from the CTL admin account. Yeah, the only, I think, in about 10 minutes or so, and then for the next 10 minutes, we'll have a lot of people joining and just making sure everyone can join okay, and that the presenters are set as co-hosts to share screens.
Yeah, okay. And I'll just monitor the chats while you're
perfect.
presenting.
Yeah, and do you have the link to the question and answer Google Doc?
Yes, I'm just gonna go look for it right
now. In the past, we haven't had enough questions that we really needed to collate it, but it would be nice just for to refer back to as they come in through the chat. If they get it, a lot of times they'll get answered in real time or fairly easily at the end without using Google Doc.
Yeah, definitely.
And thank you so much for your help.
Yeah, no worries. I'm really excited. I don't know what's gonna happen today.
In terms of the way everything will work.
Content, yeah.
Yeah. I have to give the third presentation, so hopefully people are awake by then. Perfect. All right, I'm gonna remute myself, and I paused the recording, and I'll make sure to, when Maya starts speaking, I'll start it again. But just if you can remind me to restart the recording if I've forgotten to.
Okay. Yeah.
Good morning.
Good morning.
Or good afternoon to you. How are you?
Yeah.
I got to look over a draft of your talk. The draft of your talk, it looks excellent. And so, do you want to go ahead and check that you can screen share?
Yes, just check it.
And thank you again for presenting and for kicking off the presentations.
You're welcome. I hope it makes sense. So something is up here. So my Zoom just disappeared. Okay.
Perfect.
Great.
Any other questions on your end, Lars, about how the webinar will be run? Maya Peterson's going to say a few words right at the beginning to introduce the three of us.
Okay, that sounds great. Then yeah, I think we'll figure it out as we go, right?
Yeah, it's run fairly smoothly in the past with around 100 attendees. Hi, Thomas.
Hi there. Can you hear me?
Yes, I can hear you great. And you should be your co-host now, so you should be able to share your screen. You want to try? And I got to look over your draft slides, and the talk looks excellent.
Hello.
Yes, can you hear me, Thomas?
Yeah, can you hear me now?
Yes, I can. I can hear you great.
Okay, good.
Do you want to try sharing your screen real quick?
I could do that, yes. Wait a second. Okay.
Perfect.
Well said.
All right, looking forward to it. And Maya
Yes.
will introduce the three of us quickly at the beginning before Lars, then you, then I will present.
Super. See you in a little bit.
Yeah. Hi, Mark.
Hey, Andrew.
You should be set as co-host now, and people then.
Great.
And I'll during my presentation, I'll just call on you to jump in. Thanks so much for
Okay,
saying a few
perfect.
words.
Yeah. And then I do share screen, or do you just move for me?
I'll just move for you, just because.
Yeah, that's easy.
Slides.
So I don't need share screen then, right?
No.
Okay.
All right, let's get started. Okay.
You should be able to share your screen, Maya.
Great, thank you. Hold on, I have to press the right place here. All right. All right, hello everyone, and welcome to the next in our webinar series in the Joint Initiative for Causal Inference, Spring 2021. I think I've seen many of you before. For those of you who are new, just briefly, a little bit about this joint initiative. This is a collaborative partnership between the University of California, Berkeley, Novo Nordisk, and the University of Copenhagen. And we're really working together to expand knowledge and practice of sound scientific inference and develop methodology really with the vision of increased and better use of data for evidence generation. So an emphasis on both causal methods and good methodology with specific objectives of engaging with regulatory agencies, industry, and other partners to use the causal roadmap and including targeted machine learning methods, inform clinicians about best practices for causal inference, showcase some of the scientific potential of causal inference, and develop software to facilitate dissemination and sound analysis. So we've had a number of webinars this spring. These are all available on our website and are recorded. So we began with a webinar on competing risks and methodologic developments, the webinar on longitudinal mediation and its clinical applications. Most recently, interesting series of talks on methods for the integration of observational and randomized control trial data. And today we'll be talking about applications of the causal inference roadmap to diabetes and dementia dynamics using Danish Health Registry and randomized control trial data. So we have three wonderful speakers today. First, we have Dr. Lars Lauraket, apologies for the pronunciation, at Novo Nordisk, who's going to be speaking first on understanding and misunderstanding Alzheimer's disease based on observational data. After that, we'll have Dr. Thomas Gerds from the University of Copenhagen speaking on Cox regression with time-dependent covariates, no questions asked. And finally, Dr. Andrew Mertens from Berkeley speaking on causal effect of second-line diabetes treatments on dementia, a roadmap for longitudinal causal analyses. So just as a reminder, our Q&A format, please feel free to type any questions into the Zoom chat or YouTube live chat. And then we'll have a moderated Q&A at the end of the talks. And if we don't get to your question, we will answer it later. But we've, in the past webinars, I think got to most of the questions. So please ask away. All right, welcome everyone. And without further ado, I am pleased to hand it over to Dr. Lars Lauraket. Could you tell me your pronunciation of your name though, please? I apologize for that.
No, it's perfect.
Perfect, excellent. Okay, thank you. Over to you.
Okay, so do you see my screen?
Yes, perfect.
Great.
Great. So yeah, so thank you so much for the invitation to speak here. So I'm really happy for the opportunity, but it's also interesting because I'm not an expert on causal inference. I know only the minimal amount that you need to know as a statistician about causal inference. I also don't know a lot about diabetes drugs. But I do know something about Alzheimer's disease. That is something I've worked on for quite some years now. So I will talk about how to try to understand Alzheimer's disease based on observational data and some of the problems that you may encounter there. So I think it would probably be good to start, so there's a disclaimer here that my views are my own. So it would be good to start with a brief introduction to what Alzheimer's disease is. I think most of us have a pretty good understanding that Alzheimer's disease is a disease where you essentially lose your ability to remember things, and subsequently you will sort of be so cognitively impaired that you will lose your ability to independently perform your activities of daily living. If we look at what happens in Alzheimer's disease, then here we see a cross-section of a healthy brain. And this is a cross-section of a brain of someone with severe Alzheimer's disease. And you can see from this that it is a pretty scary disease. It's quite obvious that that this is a disease that will impact your ability to think. But if we zoom in here and look at the molecular level, what's going on is two very specific things that we always see in Alzheimer's disease. We see these brown things that are in between the neurons. So these are amyloid plaque. And then we see these blue things that are inside the neurons. These are tau tangles or neurofibrillary tangles. And I think over many years of research, there is now a general consensus that amyloid plaque may be a little bit toxic, but it's not really what's driving the disease. Amyloid plaque seems to cause tau tangles to form, and then the tau tangles, they really drive the disease, causing the neurodegeneration that we see on the brain here on the left-hand side. So in this slide, we basically have sort of the key component of Alzheimer's disease. We have amyloid plaque, we have tau tangles, and then we have the neurodegeneration. So in Alzheimer's disease, there is the so-called Alzheimer's pathological cascade. And this is probably the most reproduced figure in Alzheimer's research. This is from a paper by Cliff Jack from 2010. And at that point, it was really sort of a hypothetical model. So it was based on sort of some observations here and some observations there. And then Cliff Jack really tried to put this together into a model that described what happens in the disease. So the model describes what happens in someone who will get Alzheimer's disease. So first, they will be cognitively normal. But while they're still cognitively normal, we begin to see a biomarker become abnormal, namely a beta biomarker. So that's amyloid beta. That's a measure of the amyloid that I showed you earlier. That becomes abnormal, and it actually becomes very abnormal while you're still cognitively normal. This is followed after a while by what is called here tau-mediated neuronal injury and dysfunction, but basically abnormal tau biomarkers. And this is then followed by abnormalities in brain structure. So you can begin to detect these this atrophy of the brain, that the brain is shrinking in certain places. But once you begin to see the changes in brain structure, you enter sort of a new clinical disease stage called MCI, mild cognitive impairment. And you can say in Alzheimer's disease, mild cognitive impairment is primarily characterized by a memory deficit. So you begin to see increasing memory problems. And then when you begin to see abnormal clinical function, so that is your ability to perform the activities of daily living independently, dress yourself, take care of yourself, go shopping, drive a car, and so forth, then you will have dementia. Okay, so when we want to measure the impact of Alzheimer's disease, we really measure sort of the end products. So you can say we can measure the biomarkers, and a lot has happened over the last decade. So we now have quite good biomarkers in Alzheimer's disease, at least compared to most other brain diseases. But when we diagnose patients based on, that's sort of the clinical impact. That's the impact it has on their life. And the way that we measure this impact, it's quite simple. It's the same tools that has been used for a very long time. So here's an example. It's a mini mental state examination. So it's basically a collection of 11 items that are different questions, and I'll just take a single one here, the last one. So the patient is shown these two overlapping pentagons and is then asked to reproduce that on a piece of paper while being able to look at this. And if the patient succeeds in this, the patient will get a point. And if the patient fails, he or she will get 0 points. So this is a scale that goes from 0 to 30. 30 means that you got everything right, and 0 means that you got everything wrong, and you are quite severely impaired. Another type of scale that is often used is this one here, the clinical dementia rating, which is based on a structured interview. And then you basically assess the patient in 6 different domains. So you have a memory domain, an orientation domain, judgment and problem solving, community affairs, home and hobbies, and personal care. And you basically assess the impairment on each of these domains, and then you map that onto a clinical dementia rating global score, which is what we see at the top here. And if you score 0, that means you have no impairment. If you score 0.5, that usually means you have a mild cognitive impairment, and if you score 1 or above, you have dementia. So this is another type, another way of measuring. A final example here is an outcome scale that has often been used in clinical trials in Alzheimer's disease, the ADAS-Cog, which is very similar to the mini-mental state examination. It's just a bit more elaborate and a bit more sensitive. So this is really how you measure the impact of Alzheimer's disease. But maybe we should get to some patients and some data. So 2 women walk into a memory clinic, and this is not the beginning of a bad joke. So one of them is 74 years old, and the other one is 77. And they both have memory problems. And when they're tested at the memory clinic, they both score 28 on the MMSE and get a clinical dementia rating of 0.5, meaning that they have mild cognitive impairment. So you can say they're approximately the same age. They both have memory problems. They score the same on MMSE, and they both get the same CDR score. So for all practical purposes, these 2 women, they're identical. So I didn't just make these 2 examples up. So I actually have data from them. So one of them was followed for 8 years since baseline, and these are her cognitive scores on MMSE. And what you can see here is that she scored 28 to begin with, and then she's actually quite stable. She goes a little bit down, then a little bit up, and she's quite stable for 7 years. And then we begin to see a serious decline here after 7 years. Now, the other one with the same clinical scores and sort of the same age, she was followed for a little more than 4 years, and this is her course. So we see a much stronger decline initially, and then after a little more than 4 years here, we actually see that she has declined so much that she would score at a level that we would characterize as moderate to severe dementia. So you could say at this stage here, you're not able to take care of yourself. You need someone to take care of you 24/7. And that's quite a big difference when compared to the other one, which is probably still at a mild cognitively impaired stage here. So this is of course interesting that there is this large difference. One of them is declining much faster than the other, and you could ask, well, why is this important? Why does it matter? And it of course matters to the patients. And if you could tell a patient that you may not remember things like you used to, but you can still do everything that matters to you in life, and you will be able to do that for the next 5 years. Then essentially, you're probably going to book that vacation that you dreamed of and try to live your life to the fullest. Whereas if you're told that within 4 years you will be so severely sick and incapacitated that you won't be able to take care of yourself whatsoever, then maybe you need to get affairs in order. So it's of course important for the patients, but it's also important when you do clinical research, and especially if you do interventional clinical trials where you test drug candidates, because this heterogeneity, it gives rise to a lot of noise, and that's one of the reasons why we need so many patients whenever we try to test a drug in Alzheimer's disease. It's simply so noisy, and there are so many, the patients are so different. So it's really, really hard to detect a treatment effect because there is so much noise. The other aspect is that the patients if we have a drug that we assume is disease modifying in the sense that it slows or maybe stops the progression of disease, then we really need the patients on placebo to decline in order to show a difference. If they just remain constant and do not decline, then we will never be able to show a difference. And that would really mean that if we have a lot of patients that do not decline over a 7-year period in a clinical trial, then basically we will have to make clinical trials that are so long that it will not be economically viable, even if you manage to show that you have a successful drug, and it will lose. It will be basically impossible to make the money back because the trials are also so expensive. So it's really quite important to understand this, to understand what is the cause of this. So I've collected a few different explanations that we could try to look into. One of them is genetics. So some of this may be explained by genetics. So I have a paper here. It's called Enrichment Factors for Clinical Trials in Mild to Moderate Alzheimer's Disease. And if you look closely, you can see the last author's name, and you can see that I probably think that this is a really good paper, and it found something important. So let's look at something that it found here that was reported. So in the paper, there is this figure, and it shows data from a phase 3 program in Alzheimer's disease, placebo, patients on placebo, and then how what their profiles of change from baseline look like on different scales. And you recognize the ADAS-Cog that I showed earlier and the MMSE, but there are also some other scales. So this plot has been made such that down is deterioration, so down is bad, and up is good. And there are 3 different curves. So the placebo group was split into 3 different groups, namely based on their ApoE epsilon 4 carriage. Some of them were epsilon 4 plus. So that means that they have this allele of this gene ApoE that is also called just ApoE4. They have 2 of those. They inherited one from their mother and one from their father. So the green group here is epsilon 4 plus minus. So they only inherited 1 copy and 1 copy of the gene that wasn't this E4 allele. And then there is the epsilon 4 minus, where they don't have this ApoE4 allele. Now, ApoE4 is the primary genetic risk factor for Alzheimer's disease. It's a variant that's quite common. So between 20 and 25% of the general population will have at least one copy of this gene. But it is really well established that this is a major risk factor for disease. If you have 1 copy of it, you have an increased risk, lifetime risk of developing disease lifetime that is around 2-fold, maybe 3-fold of what you have if you don't have the gene. And if you have 2 copies of it, it's more than 10-fold the lifetime risk of developing disease. So this is quite important. But if we just look at what I found here, and what we found in this paper, is that the patients treated on placebo that were homozygous, so they had 2 copies of the E4 allele, they seem to have a stronger deterioration. So they seem to progress faster. So this is of course interesting to know, and you can use that in clinical trials. And from a causal perspective, it's of course genetics is also quite nice, because we have sort of this property that genes are randomly assigned to individuals from their parents, and we also know sort of the causal direction that it's not something else that influenced the gene; it's the gene that came first. There are, of course, still some problems with causal interpretation in genetics, but it's much simpler than many other things. So another example here. This is very recent. Actually, this was only published online yesterday. So this is a new study that finds a SNP, so a polymorphism in a gene called IN1, that's associated also with Alzheimer's disease risk, they found that this SNP is also associated with what they call faster amyloid beta-associated tau accumulation and cognitive decline. And what they show here is basically that on ADAS-Cog and some other clinical scales, that the individuals with this risk variant, that they have a faster annual change. On ADAS-Cog here, up is bad, and on the two others, down is bad. So it seems that this is another genetic risk factor that actually seems to somehow maybe accelerate the course of disease or the decline. Again, this is nice. So you have some more information to explain why you see the differences. Now, another source of the heterogeneity could be something like socioeconomic characteristics. So I think in this forum, where I imagine that most people are quite highly educated, I think we can all agree that something like education is a good thing. And we of course know that education is associated with it's associated with better health, with longevity. And if you look at the data sort of in the right way and squint a little bit, you may also be able to see that longer education is associated with lower incidence of Alzheimer's disease. So the problem is, of course, that it's also simultaneously associated with longevity. So you have sort of longer time to get the disease. And you can say, I think many of us believe that this is actually partly a causal effect, that if you took high school seniors and you randomly assigned some of them to be able to continue education and some of them couldn't, then I think, so personally, I think that probably the ones that were randomly assigned to get a longer education, that they would also have better health outcomes in the long run. But in Alzheimer's disease, it also turns out that there is something that's a bit weird, and that is that it seems that education does not affect cognitive decline with aging, or does not slow it. I really like papers like this where they just put the conclusion in the title. It makes it very easy to find them. So this is of course not great news for us here in this forum, but it's actually even worse, because there is a paper here that says that higher education AD patients experience faster cognitive decline. And there are many papers like this. So I just have another one here where it says that higher educational attainment is associated with a slightly accelerated rate of cognitive decline in Alzheimer's disease. And if you search for this, I think you will actually find hundreds of papers that look into this problem. And I think the vast majority, so I've seen many papers that find this association. So this is of course interesting, and it may also give us an explanation for some of the heterogeneity we see. Okay, so the first or the third example here that I will present in the last one is related to Alzheimer's disease treatments. So in Alzheimer's disease, there are two approved classes of medications, the so-called choline esterase inhibitors and a drug called memantine. And I'll just focus on the choline esterase inhibitors. So both types of drugs are symptomatic, so they don't alter the course of the disease. But if you look at the Cochrane systematic review, it concludes that the choline esterase inhibitors are efficacious for mild to moderate Alzheimer's disease. So there has been many clinical trials, and they have clearly shown that there is a benefit of these drugs. But again, it's symptomatic. When you stop the treatment, it seems like that you lose all of the effect. A natural question to ask is, of course, what is the long-term consequences? And again, here a wonderful paper where the main topic is in the title. Could choline esterase inhibitors be harmful over the long term? I think this is a very valid question to ask, because this is seen with many drugs, and this is a drug that modulates the neurotransmitters, so it may actually alter some sort of homeostasis in the brain that could potentially be harmful in the long term. I think that's very fair, and actually there are many studies of this also, and here is a recent one. So the association of concomitant use of choline esterase inhibitors or memantine with cognitive decline in Alzheimer's clinical trials. And their results here, so the important thing is at the bottom, is that a meta-analysis showed that those receiving choline esterase inhibitors or memantine were associated with significantly greater annual rate of decline on the ADAS-Cog than those receiving neither medication. So this is potentially worrying, right? That we have these drugs and we see that there is a benefit of them based on the trials that have been done. But when you look at just data from clinical trials, where patients, they came in based on whether they could be on choline esterase inhibitors or memantine, there is this association that they seem to decline faster. So this is really something that one should consider, right? Now, that was a lot of examples. So now I'm getting to the meat, and my point with all of this is that one should always remember that Alzheimer's disease is a dynamic disease. It's a progressive disease. The patients, they progressively get worse, but it's also a very slow disease. So from the initial symptoms till the patients, they are so sick that they will actually die from the disease, it will be often more than 10 years. So it is a very slow disease. But what is interesting about sort of all of the dynamics of Alzheimer's disease is that the diagnosis of Alzheimer's disease has also been sort of a dynamic quantity. So it was originally described in 1907 by Alois Alzheimer, where he described this first case of pre-senile dementia, which was then later renamed to Alzheimer's disease. And for many years following this, Alzheimer's disease was a term that was reserved for the early onset dementia, so the pre-senile dementia, as opposed to the senile dementia, which was just considered a natural consequence of aging, that you would lose your cognitive ability if you lived long enough. Then over the last decades, there has been refined diagnostic criteria, and they've been changed over and over again, and sort of groups of patients that seem to have specific types of dementia, they were grouped together, and they were taken out of this Alzheimer's disease diagnosis. So we have sort of a more clear type of disease. And more recently, and this is very important, I think, in 2018, the National Institute of Aging and Alzheimer's Association, they published a research framework where they proposed a fully biological definition of Alzheimer's disease, which is based on biomarkers. And it basically says that you're on the Alzheimer's continuum if you have amyloid, and you have Alzheimer's disease if you have amyloid and tau. So if we just go back to the first example I showed you here, the paper that I co-authored, then this was done based on trials that did not require biomarker evidence of Alzheimer's disease. So that means that we recruited some individuals that had what looked like Alzheimer's disease, but in fact they didn't have it. They had something else. Now, to make matters worse, this clinical program was run simultaneously with many other clinical programs that had requirements for amyloid positivity. So they should have evidence that they actually had the pathology of Alzheimer's disease. So the patients that screened for those trials but failed because they didn't meet the criteria, they could just pick among the other trials that were there that didn't require amyloid positivity and then they could enter those trials. So that means that not only did the trials without biomarker requirements, not only did they recruit patients without amyloid and Alzheimer's disease, but they actually recruited many more than they would have because they were in competition with the other trials. And if you think about it from that perspective, then you may actually see something else than ApoE4 homozygous progressing faster in this plot. Because actually, if you have symptoms that are consistent with Alzheimer's disease and you're ApoE4 homozygous, then there is very, very, very high likelihood that you actually have Alzheimer's disease. So these are patients where we are really in this situation that if they live long enough, they will get amyloid in their brain. If you're an ApoE4 heterozygote, so there is a good chance that you do have Alzheimer's disease if you have symptoms consistent with Alzheimer's disease. But if you look closer at these patients, if you examine biomarkers, there is also a proportion of them that don't have Alzheimer's disease. And if you're an ApoE4 non-carrier, as we saw in these trials, then there is actually a substantial probability that you don't have Alzheimer's disease, but you have something else that's causing your cognitive symptoms. So with that perspective, you could say, given the diagnostic, the way of diagnosing Alzheimer's disease today based on a biological approach, then what we see here is maybe not a faster decline of ApoE4 homozygous. Maybe we just see that patients with Alzheimer's disease, they decline faster than patients without Alzheimer's disease, which was sort of a fact that was generally well known, that if you have sort of these symptoms consistent with Alzheimer's disease, but you don't have amyloid, then on average, these types of patients, they tend to decline slower. So maybe that really didn't explain too much of this. Now, to address some of these other examples I gave, I will just talk a little bit about modeling the disease progression in Alzheimer's disease. So I showed you data from 2 women earlier. So here I show you a lot of data from the ADNI study, that's the Alzheimer's Disease Neuroimaging Initiative. So you can see here I have data on the ADAS-Cog. It goes from 0 to 85, and if you score 0, you got everything right. If you score 85, you got everything wrong. And these patients, they've been followed, some of them for up to 14 years. So really, really long longitudinal follow-up of these patients. And they're colored according to their baseline diagnosis. So the yellow ones are cognitively normal. The dark red ones, they have dementia at baseline. And then there are these 3 groups in between: significant memory concern, mild cognitive impairment early, and a late MCI group. Now, what you can say when you look at data like this is that, first of all, you can appreciate that there is a huge variability. When we're doing a clinical trial, we will typically look for a treatment effect that is between 1 and 2 points on ADAS-Cog, and you can see just there may be 20 points or more difference just within a single of these baseline groups at baseline. So quite substantial. But if you think about the baseline groups, then you can say, we know that before dementia, you're mild cognitively impaired, and before that, you're cognitively normal. So you could ask, could I sort of somehow use this data to estimate the time difference? So how long does it take for an average person with late mild cognitive impairment to progress to sort of the average dementia state? And it turns out that you can do this in a data-driven way. So what I show you here is sort of a disease progression model that I've developed, where it just tries to align this to minimize the vertical variation along sort of a course, and so in such a way that you see sort of the most consistent pattern of variation. And time 0 on this new timeline here now represents just the average baseline status of the cognitively normal group. And then we can basically see here that the significant memory concern group, that seems to be, maybe 3.5 years later than the average cognitively normal group. But you can also see sort of the relative timings that from the late mild cognitive impairment to the dementia, we have approximately 5 years time progression. So now when I've done this, you could of course ask, could you do the same thing on the patient level? So there is a large variation between the patients here. So let me see, can I move this? Oh, sorry. Okay. Let's see. Okay, so now so you can do it on the patient level and just sort of move the individual patient trajectories back and forth. And you get sort of this nice timeline where you get a quite consistent pattern of variation. So I have this problem with this on my screen. I don't know if you can see it. Zoom bar.
Looks good, Lars.
Okay, so I'll try to just ignore it. Okay, so you may ask, what actually happened here? I just showed you an animation, and it seemed to sort of find a pattern in this haystack of data. And what I did was that I basically took the ADAS-Cog score for subject I at visit J, and then I modeled it, and I said, well, there is a general mean trajectory of cognitive decline, and this is a function, and it takes a time argument. And this time argument has the time since baseline that I showed you originally, but then it includes sort of a time shift parameter that corresponds to the subject I's time since cognitive normality at baseline. So basically, I take the individual patients and move them across this continuum and predict for every patient how far are they in disease. And then I also include sort of like in the spirit of a classical linear mixed effects model, a term describing the random variation. The sort of this xi here is the consistent deviation from mean over time, and I also have a term describing the independent measurement noise. So this is very similar to what you would do with a linear mixed effects model. The only thing is that I have here a nonlinear function, and then I have this effect where I model the variation on the x-axis. So basically trying, just based on the shape of the cognitive decline, trying to align and figure out where is a patient disease based on this. So this is of course a model. It's not the truth, but it's when I've looked at it and tried to validate it, it is actually quite a bit better than not modeling this latent time. So if we go back to the second course that I looked at for heterogeneity, so the socioeconomic characteristics, then we can ask, well, how does this work if we look at this from this other perspective? If we look at this predicted disease time that I have here, how does this work? And I actually know the education of these subjects in the ADNI study, so I've grouped them here into 4 groups. One which is 4 to 12 years of education, 13 to 15, 16 to 17, and 18 to 20. And if we look at sort of the individual mean curves, then we see what you probably would expect. We see that the longer education you have, the better you do on this cognitive test. So it's a small difference, but it's definitely there, and it is actually in the order of magnitude of these couple of points that we would normally look for in a clinical trial where we're looking for a treatment effect. Now, another important thing to note is that in a clinical trial, we actually have an inclusion criteria, and we will typically have a cognitive cutoff of some scale. So if we imagine the cognitive cutoff is, for example, that you should score between 20 and 30 on the ADAS-Cog, then we can see that if we just entertain the idea that this is close to reality, what I show here, that we actually have predicted the timeline of cognitive decline in Alzheimer's disease, then we have the chance to recruit individuals that are very early in disease over here. So these individuals, they're characterized by having no decline or very, very slow decline. We would also include some individuals that are on the other side of mean curves. So they are later in disease, and they're characterized by having a very, very steep decline. Now you can ask, are there other differences here? Well, one difference is that there is a larger probability if you find a patient over here, they're more likely to actually have a lower education than if you take a patient over here. So a patient with a higher education is, on average, a little bit better to compensate and score better on a cognitive test than someone with lower education, which means that they can actually be recruited into a clinical study later into their disease, where they also tend to decline faster. So one explanation for this fact that length of education seems to be driving the progression of disease and giving an accelerated clinical decline may actually be just that the patients, they're able to compensate later, they're diagnosed later, and they enter clinical trials when they're later in disease.
Lars, this is a beautiful talk. I just want to give a quick heads up on time because I think we're running just a few minutes over. But
okay, so I only have a couple of slides left, I think. So so you can say, what about cholinesterase inhibitors? So I also talked about that. And if we just go back to the data here, it's actually exactly the same story. If we believe that the cholinesterase inhibitors, they are efficacious as they've shown to be, then if you include in a study a patient on a cholinesterase inhibitor, then you would actually expect that they did better than they would do better than what they would have done if they weren't on a cholinesterase inhibitor. This also again means that they will be able to be included later into disease where they have a faster rate of progression. So there is sort of a competing explanation for that. That you would actually expect to see that phenomenon for an efficacious drug. Now, the final thing here that I will touch on is this very new paper where I think there is it's quite interesting because we saw this figure here, and you could say, well, I've just shown you that if you're able to compensate somehow, and if you can be above the mean, then that could also be an explanation for why you see a faster rate of decline. So could that be the case here? And we actually see that they do all the right things in this paper. So they use the biomarker definition of Alzheimer's disease. But what is interesting to see here is that if you look at the brain scans here, which are tau PET scans, which are really measuring, it's the gold standard of measuring the pathological progression of disease. It actually seems like the one that have the BIN1 risk gene, that they have more tau in their brain compared to those who don't. So an alternative explanation here could actually be to reverse the conclusion here and say the BIN1 risk gene actually causes less cognitive decline in the early stages of Alzheimer's disease. So these patients are better able to compensate. So when you compare them, when you directly compare them to the references, then it seems like they decline faster, but it's actually because they're later in disease. So that could be a competing explanation for this. So just to quickly wrap up here, I think the take-home messages here is that one should always consider this, that the Alzheimer's disease diagnosis is changing over time. So if you look at historical data, that is really sort of an important contributor of variation in data. The second thing is that the rate of decline in Alzheimer's disease changes as the disease progresses. So whenever you want to study progression rates in Alzheimer's disease, you should always consider that your findings, they could be confounded by progression, and try to sort of see if that makes sense. And the final thing is that I think it's always helpful, if you can, to try to include these latent variables in your models, to try to model that you don't know where a patient is in disease when they come into a study. The models will still be misspecified, but they will be a little bit less misspecified, and inference will be more robust. So that was all I had. So thank you for listening.
Beautiful. Thank you so much. So we're just a little behind, but not too bad. And it was a beautiful talk. Does anybody have any questions? Please feel free to type them into the chat. You have explained things so clearly that there were no questions from the audience at this time. If anybody does think of a question later, feel free to type it into the chat. Otherwise, I think we will move on to our next speaker, Dr. Thomas Gerds. And thank you, Dr. Rackett. Thomas, you are sharing. Wonderful.
And you can also hear me?
We can hear you. Yep.
Great. Okay, thank you very much. I'm considering my talk a warm-up act for Andrew's presentation later on. And I'm presenting here from the dungeon of Bronsoy Palace about my thoughts about the Cox regression model with time-dependent covariates. And I want to start out saying that I never liked that model. And talking to my colleagues, Torben, Helene, Thomas, and Paul during the last 2 weeks, which was very interesting discussions, has not changed my opinion about that model. And I want to share some of our discussions today. And to begin with, I want to go a bit earlier than the Cox model and start 7 years before Cox actually, Sir David Cox invented the Cox model. And this is another famous person, Sir Austin Bradford Hill, and he made this very interesting contribution to causal inference, maybe the first one where someone was actually directly talking about causal inference. And here on these two sentences taken from his paper, he clearly distinguishes between causality, where he doesn't have the skill or interest to be an expert, and causal inference, which is what his presentation is about. And here he directly speaks it out that he's interested in whether the frequency of the undesirable event B will be influenced by an intervention on the environmental feature A. So it doesn't have to be an environmental feature, it can be a treatment. But what is interesting is he's not talking about the rate of the undesirable event, but about the frequency. So he's directly speaking in the same way as we think today. Now, even earlier, maybe the first 22 years before Cox in 1950, the same author together with Richard Dahl presented this very useful result regarding the connection between lung carcinoma and smoking. And they write in their paper in 1950 that the simplest comparison that can be made in order to show whether there's an association at all between smoking and carcinoma of the lung is this 2x2 table. And now when we think about a 2x2 table where we have asked patients of lung carcinoma and other patients of no lung carcinoma regarding their smoking habits, then it's quite clear, in order to come to the situation, to get the question regarding how much did you smoke in your life, you need to survive until that day. So in fact, it's conditional on survival until the day where you get the question regarding your smoking habits. And if you think a bit more about it, and that was presented quite nicely by Prentice and Breslow in 1978, there is a connection between the case control study and the time to event analysis. And if you think about it, then this is a Cox regression model with time-dependent covariates, and the only time-dependent covariate is the smoking history in this case. Now, 14 years after Sir David Cox came James Robbins, and he made this 120-page long contribution where you can find more or less everything. And if we read carefully, we have to read carefully in that paper because otherwise we get lost. But if we read carefully, we can see here a quite clear statement regarding the time-dependent Cox analysis, where even if, and he calls that the fully randomized, measured, causally interpreted structured tree graph. So if, let's say, if the time-dependent Cox model is correct, then we still cannot test the null hypothesis that the exposure has no effect on the outcome if we control for smoking history or some other time-dependent covariate. So this is quite valuable. This paper, which requires some time for reading. Now let's skip to today. Today we are working in this very nice joint initiative group, and we are talking about data like this, shown in this figure here. We have a treatment process history, which we call A bar, and at time t, we can look back at the values of the treatment at times before time t, maybe between some time 0 and time t, and then we have a covariate process history, so which is using the same notation. And then when we are facing analysis of data like that, then we have to deal with right-censored data. So we cannot observe these processes for all patients equally long. And also these processes are truncated at the time of outcome or at the time of death. When we use this notation, then we can write down the outcome-specific hazard rate at time t in form of a Cox regression model with time-dependent covariates. Here we are using lambda naught of t as usual for the unspecified baseline hazard function. And then we have the beta coefficient connected to the treatment history at time t and another gamma coefficient to the covariate history at time t. And there may be a plus, there may be also interaction terms, doesn't matter so much. What is interesting is that you can estimate the hazard ratio in various different ways. And the classical way would be the maximum partial likelihood, but you can also estimate the beta coefficient almost with the same result using Poisson regression by making a discretized version of the baseline hazard, or using conditional logistic regression using the nested case control design. And that justifies this is related to the subtitle of my presentation for today. Is it possible, can someone ask a clinically meaningful question such that the beta coefficient is the answer? And I've been thinking a lot about exactly this question for the last 2 weeks, and I did not come up with many very relevant examples. And maybe I can talk about that at a different time point. But for now, let's say it's very difficult to ask a question such that beta is the answer. Now, 3 years ago, and that is when our collaboration with Novo Nordisk started, and we were analyzing the Danish registry data together with Sarah Friedrich, who is here today, and she made the analysis. And this is a figure describing the analysis. So we have a nested case control design. Our outcome is the dementia as defined by the registry data of the Danish registries. And we made this interesting design which you look at, which is the Lexis diagram with the calendar time on the x-axis, and then the age of the people on the y-axis, and then we include diabetes patients 5 years after their first usage of a second-line diabetes treatment, and we use this 5-year waiting period in order to be able to summarize the treatment history of each patient at each time point in the follow-up period for the previous 5 years. So we want to make the exposure window equally long for each time point in our follow-up period. And in that way, we got to this result here. We got a lower rate of dementia was shown with increasing exposure to the drug GLP-1, and we have a hazard ratio of 0.89, and then some confidence interval, which is indicating significance. And this 0.89 is connected to a 1-year increase in duration of GLP-1 exposure in a 5-year exposure window. If we look at the model here, then we have a Cox regression model, and here to show that we are not conditioning on the future, we are conditioning on the covariate history 5 years earlier than the time point where we evaluate our hazard rate. And then we compare the treatment history, maybe can have the value 2 years in the nominator, and in the denominator, then it would be the value 1 year, and this would be a 1-year increase. However, the value 0.89 does not have a nice interpretation. And based on this analysis, we cannot even rule out the possibility that the GLP-1 increases the risk of dementia. Our best guess would not be that it does increase the risk of dementia, but it could happen. And therefore, we have to state that the result is inconclusive. And that is not so nice. Now, the interpretation of beta is hampered, and that is well known. There are a lot of papers about this, and there are many different words for the same phenomenon. So when we look up in this classical book by Carl Fleisch and Prentice, then any covariate which is an internal covariate is very difficult to analyze in the survival setting. Treatment in our case is a time-dependent covariate. It is an internal process which does depend on the patient's frailty and is also affecting the patient's frailty. So it's really not so easy. And then there are these all these different terms: healthy worker effect, selection bias, depletion of the susceptible, and so forth. And there are some references in the bottom of this slide, but there are many more very interesting results on this. And what I wanted to mention is, again, back to the subtitle of my talk. So what is the question? So lack of definition here. When is the time of intervention? This we have not defined in our study. And it's clear that when we stand at time point T, then we can intervene on the current diabetes treatment, but we cannot go back and say and we cannot change the history of the patient's treatment usage. And that's a big problem. So when we want to ask a meaningful question, then we have to first go ahead and start the time of intervention. But there's one more thing I want to mention here, and that's these ICH statements, which are about estimates. And here we learn that one has to be very careful when treatment effects are comparing outcomes in a subset defined by occurrence of a post-baseline event, because that leads to confounding and selection bias. And of course, when we think about the hazard ratio, then the hazard ratio is about the patients at risk at a certain time point during the follow-up. And at that time point, the people who are not at risk anymore have been selected away due to outcome, due to death, and due to censoring. And all these things can of course affect the results of our study. So my conclusion is that the hazard ratio cannot fulfill the requirement here of the ICH statement. And we can worry, are we stuck here? But maybe we're not. And we go back again 7 years before Cox. There is Sir Austin Bradford Hill, and he says, okay, we could do everything here in the lab and see if we can identify the causal links in the lab. But on the other hand, we statisticians, we should not sit around awaiting the results of that research. He says we may, depending on the circumstances, we may have to unravel the whole chain in order to make an understanding of the causal inference. And there's some work in progress here, and finally it has appeared on arXiv. It has only 86 pages, not quite as long as Robin's seminal paper, but it is about unraveling the chain of action here, where you look at the product integrals, which are integrating over time, and then there are the A's here, these are the treatments, and then the L's are the time-dependent covariates, and then C would be the censoring, and D would be the death or the outcome. And all this together can now be analyzed by a TMLE, which is adapting the time-dependent pattern here. And what is interesting, everything here is in continuous time, because we need to be able to take into account in the Danish registry data, for example, that patients will have changes of their treatment at patient individual time points and not at scheduled time points, as would probably be the case in a planned randomized trial. Now, before we can apply the TMLE work, we need to define what we want to estimate. That's one of the first things of the roadmap. So how do we actually define a cumulative treatment effect? And then thinking about that, it is much easier to think about a transient exposure, something like mobile phone use in a car and the relation of that to an accident of the car, as compared to thinking about the effect of a drug that accumulates over time, but where over time a lot of other things can also happen, namely covariates can change and the outcome can happen and death can happen and so forth. So it's really difficult. But it seems that since we're interested in the long-term effect of the GLP-1 drug on dementia, then we would have to define dynamic treatment groups. And this is what the presentation of Andrew is about. So stay tuned. My final slide here is just summing up. If you have a very nice data set and no one is asking a question, then you may end up using the Cox regression model with time-dependent covariates, because this seems to fit to the outcome and the nature of the data. But if you haven't asked a question, then you cannot expect an answer. Okay, thank you very much for your attention.
Thank you so much, Thomas. That was a beautiful talk again, and a lovely bridge between the two. Any questions from our audience on Dr. Gerd's talk? Okay, well, I think that's a nice segue then. And next up, we'll have Dr. Andrew Mertens, who will be talking about some work done laying out the application of the causal roadmap to this problem with the registry data. And this is part, again, of an ongoing working group through the joint initiative. So take it away, Andrew.
Thank you, Maya, and thank you, Thomas, for setting the stage for this talk. I'm Andrew Mertens. I'm a research data analyst at UC Berkeley, and I've been working with the Joint Initiative for Causal Inference to design a roadmap to estimate the causal effect of second-line diabetes treatments on dementia. And today, I want to use this specific example to show you how the causal roadmap is applied to move from a specific scientific question to a statistical estimate that answers our scientific question of interest, in contrast to, say, what Thomas set up, where it's easy to estimate a hazard ratio from a Cox proportional hazard model, but that statistical estimate doesn't answer our scientific question. It's the easy and common approach, but it gets the workflow backwards, where you work with what is common and then take that to answer what you can with the hazard ratio. Here we reverse that. We start with our specific scientific question of interest and work step by step to move from what we causally want to estimate to what we are able to statistically estimate, and what assumptions we need to make for that statistical estimate to answer our causal question and scientific question of interest. So Thomas gave some great background, but in this specific project, we're interested in how diabetes medication may decrease dementia risk In particular, GLP-1 receptor agonists, a second-line treatment, might be particularly neuroprotective of developing dementia. As Thomas laid out, the existing research is limited in that it is not designed to answer clearly interpretable causal questions. It fails to fully adjust for measured confounders, including time-varying confounders, and it uses statistical methods that require unrealistic assumptions like proportional hazards. And so our specific scientific question is, what is the effect of cumulative exposure to GLP-1 on dementia risk? Today, we'll step through the process of going from this scientific question to a well-defined causal target parameter, followed by a well-defined statistical target parameter. We'll lay out a clear understanding of what assumptions we'll need to make for the statistical parameter to have a causal interpretation. And then we'll discuss how simulations can be used to fully pre-specify a statistical estimator before taking this laid out roadmap for an analysis, registering it as a priori statistical analysis plan, and then applying it to the actual Danish registry data. And so we need a roadmap to help drive this process. And this aligns with the ICH E9 guidance on estimands. And their lexicon estimand is equal to what we call the target causal question or parameter here. So this causal roadmap is fully aligns with guidance in setting up clinical trials as well as observational analyses. And so to lay out the causal roadmap, we first start with the causal question before fully defining the observed data, discussing what assumptions are needed to identify the causal parameter or the statistical parameter under explicit causal assumptions. Then we lay out how to estimate that statistical parameter, and then how to interpret the final result and link it back to our original scientific question. So to start with, at the beginning of the roadmap, we want to lay out the target causal parameter. We have our scientific question of interest, but translating this question into a formal causal parameter requires carefully defining the ideal hypothetical experiment. If we had no limitation in money, if we were able to compel subjects to enroll in a hypothetical randomized controlled trial, if we could intervene to, say, prevent death, what would our ideal hypothetical experiment look like to answer the scientific question? And we start by defining our target population. Who would be in this hypothetical but possibly not feasible ideal experiment to answer our scientific question? And in this case, we lay out our target population as those previously diagnosed with type 2 diabetes, who are older than 50, who have been on metformin first-line treatment for at least 5 years, who hadn't previously been diagnosed with dementia, who are initiating any second-line treatments, and we're excluding those with basic bolus insulin or a pump algorithm because they would not be prescribed GLP-1 or SGLT2 or DPP-4. And then our baseline time point is the date at which the patient initiates second-line treatment on one of the drugs of interest. And so this is conceptually similar to a randomized controlled trial with rolling enrollment, where you enroll each patient the moment they switch to a second-line treatment. Now we move on to defining the treatment regimes of interest, the ideal protocols in this ideal experiment. What variables would you ideally intervene on to control and how in this randomized trial? And what variables do you not intervene on, like competing risk or adherence, if adherence to the drug is part of your effective interest? And so one option for our ideal experiment would be a hypothetical intervention on drug use at a single time point. So the baseline switch to a second-line drug. So the treatment could be those who initiate GLP-1 at baseline with an active comparator of all others initiating other second-line treatments at baseline. So in this ideal experiment, patients could still interrupt or switch treatments post-baseline. This graph at the right shows actual second-line treatment use in the Danish registry data. And as you can see over time, there's fluctuating patterns in drug prescriptions, and which means at different periods of time, different individuals are potentially switching drugs or being prescribed a different drug than they might have been a couple of years ago. But this hypothetical intervention is not ideal at getting at cumulative effects because we just know the effect of initial prescription, though the patients could switch treatments at any time. And so maybe a better option is to intervene on second-line treatment use at multiple time points. So here, the hypothetical treatment of interest would be initiating GLP-1 at baseline and staying on it for at least 5 years. And the active comparator arm would be maybe those who initiate SGLT2 or DPP4 and stay on that at least 5 years. These are two second-line treatments thought to be most comparable to GLP-1. Or a alternative comparator would be the standard of care, any second-line treatments except for GLP-1. And so this second option is the actual ideal treatment regime of interest in our hypothetical ideal experiment. And so in this hypothetical experiment for both arms, we would allow for brief interruptions on drug use, less than 9 months. This is because we hypothesize a cumulative effect of these drugs on reducing dementia risk. And this better reflects real-world usage compared to a hypothetical drug where we can mandate that patients take the drug as prescribed to the doctor without any interruptions. And so we hypothesized that this would not undercut the drug benefits, and without allowing for these brief interruptions, there may be insufficient number of patients in the actual Danish registry data for perfect adherence. We also don't want to allow permanent discontinuation. An issue in the real data is knowing when this happens. We can assess based on pharmacy refill, but we don't know the actual dose that patients are taking. And we also allow for intensification, i.e. with insulin at clinician discretion. We are not intervening in this hypothetical study on the intensification process to allow our hypothetical trial to better reflect real-world processes. In this hypothetical experiment, we would intervene on follow-up to prevent right censoring, aka we would ensure that we follow all participants until the max time point we care about, i.e. 5 years on the second-line treatment of interest. And then our ideal treatment regimes of interest are here A bar equals 1, A being the treatment node, the bar over it, meaning over the course of the 5 years of interest, equals 1, which means they initiated GLP-1 at baseline and remained on it over the course of the full 5 years of follow-up with no interruptions greater than 9 months. The ideal active comparison of interest is A bar equals 0, or initiating the active comparator at baseline and remaining on it with no interruptions greater than 9 months, also for the full 5 years of follow-up. And so now we can move to defining the ideal outcome in this hypothetical experiment. We're interested in the diagnosis of dementia, with Y denoting an indicator for dementia diagnosis by 5 years. Y of T would be an indicator for diagnosis by time T starting at baseline up to the full 5 years. In this hypothetical experiment, we're treating death as a competing risk. We're not hypothetically intervening to prevent death in patients. This is a key point because GLP-1 reduces death. That means that we will, to some extent, underestimate the biological effects of GLP-1 on dementia, as it keeps people alive and they have a greater chance of getting dementia if they don't die if they don't drop out of this hypothetical trial because they have died, the competing risk. An alternative option we could have chosen would be using a composite outcome, the development of dementia or dying over the 5 years of follow-up. And so now that we've defined our outcome of interest Y, we can define counterfactual outcomes Y A bar. This is an indicator about whether dementia would have been diagnosed by 5 years after baseline under the ideal hypothetical intervention A bar. And it's a key to note that these are counterfactual outcomes. These are not the observed outcomes contrasting the actual development of dementia among those who were on GLP-1 in the registry data versus those who were on other second-line treatments. This is the counterfactual outcome where Y A bar equals 1 would be the counterfactual dementia status after 5 years if every eligible subject had received the treatment regime, continuous GLP-1 diabetes treatment. So here in our hypothetical experiment, we're able to take everyone over 50 with type 2 diabetes initiating second-line treatment in Denmark and enforce that they take GLP-1, follow them for 5 years, and then see what proportion developed dementia after 5 years. And then our counterfactual contrast is y a bar equals 0, the dementia status after 5 years, if every eligible subject had received the active comparator. Then we can take these two counterfactual outcomes and define our target causal parameter of interest, the population level summary measure used to contrast counterfactual outcomes under different treatment regimes. Is it the hazard ratio we care most about, or is there a different causal parameter that better answers our scientific question of interest? And so the target causal parameter is a function of the unobserved counterfactual outcome distributions, not the actual outcome distributions observed in the data. The choice of the population level summary measure for contrasting the treatment and active comparator intervention could be something like the causal risk difference, which is what the rest of this presentation will focus on. The difference between the expected proportion of dementia diagnosis by 5 years if all patients had complied with GLP-1 regimes versus if they had all complied with the active control regimes. An alternative target causal parameter that we're also interested in the actual registry analysis would be the full counterfactual survival curves under both the treatment contrasted to the active comparator ideal protocol for both dementia diagnosis and death, so handling competing risks. So now that we've defined our target causal parameter, we can move on to defining the actual observed data and the statistical model that reflects uncertainty in the actual observed data we have. And so in this causal roadmap, we have independent and identical and independently distributed copies of the longitudinal data structure O, the observed data, which is a function of baseline and follow-up measure data up to the time point K, the max follow-up time. The A nodes are intervention variables. These are the variables we said we'd intervene on in our ideal experiment, with A1 being the treatment and A2 within the A node being right censoring. So we're both intervening on whether the patient gets GLP-1 versus the active comparator, and we're also intervening to prevent right censoring. And then we have a whole set of L nodes, the non-intervention variables, starting at L0, which would be the baseline non-time varying characteristics measured at the time of initiation of second-line treatment, as well as LT, the time varying characteristics. And Y is part of the L nodes because it's not a variable we intervene on. And Y of T would be dementia diagnosis by time T, with Y being the final outcome of interest, dementia diagnosis by 5 years. And then we set up our statistical model, which is the set of possible distributions for the observed data. And a key point here is we want to avoid any unsupported assumptions, work in large semi-parametric statistical models, because this is a large, complex set of variables in the observed data that we don't have a strong baseline knowledge around parametric assumptions of the distribution of these observed data. So we want to avoid any unsupported assumptions in the statistical model. And so we have these intervention variables. As I mentioned, there's the A1, the second line treatment used at time T. Here in our hypothetical experiment, it's GLP-1 versus active comparators, or neither. This would be measured via anti-diabetic drug purchase at time T. In the observed data, unlike in our ideal experiment, treatment modifications and prolonged interruptions occur over time for some persons due to side effects, due to new options becoming available in the market, etc. And then we have our A2 nodes, the indicator for still under follow-up time T. Unlike a randomized controlled trial, there's less loss to follow-up because this is a large nation-level registry. But in the Danish registry, there's still a major source of right censoring is administrative censoring. driven by variability in calendar date of baseline time points across participants. If a participant started a second-line treatment in 2018, there's just not enough time that's passed to have a full 5 years of follow-up time. Then we have our L nodes. The L0 nodes are non-time varying covariates at baseline, such as demographics or baseline medical history. And then LT are the time varying covariates, like medical histories, medical purchases, hospital admissions. And this would include death, as well as diagnosis of dementia. And so Y of T is a specific part of our observed data that is part of our non-intervention variables, L of T. Here, Y of T is the indicator for dementia diagnosis by time T. We're basing dementia diagnoses in the Danish hospital registry. Ideally, we would know the exact time of dementia onset. Dementia onset will occur before diagnosis, but we're only able to observe the time of dementia diagnosis itself. A key point is that if the times at which dementia status assessed are variable across persons and affected by the treatment, this could result in a less interesting target parameter because there's differential timing of diagnosis and basically interval censoring in the between the different arms in diagnosing dementia. So a solution is to add a hypothetical intervention to ensure comparable assessment frequency. And so this is back to defining our ideal experiment. And this is part of the causal roadmap where, as we lay out what our observed data is, we link that back to our ideal experiment and to best understand how we can estimate that causal parameter of interest. And so now we move on to formally defining the causal model and ensuring identification. This is step 3 in the roadmap, where we translate the causal parameter of interest. Here it was the risk difference at 5 years of follow-up in dementia. We translate this causal parameter to a statistical parameter under explicit causal assumptions. And so causal identification is translating this causal parameter into a parameter of the observed data distribution, a statistical target parameter. So we move from the counterfactual contrast of if everyone had received GLP-1 versus an active comparator to what we actually observe in the observed data distribution. The causal model is a tool to do this by expressing our knowledge about the data generating process in facilitating this into a translational process. This requires key subject matter expertise, such as why are patients started on GLP-1 versus other second-line treatments? What are key reasons patients switch off GLP-1 to something else over time? What are key reasons for or potential predictors of longer-term interruptions? And what are the key causes or predictors or confounders of dementia? And so this step in the causal roadmap is what allows us to formally incorporate subject matter expertise and background knowledge into our statistical analysis plan. And so one of the identification assumptions is the randomization assumption. Here it's laid out for a single time point intervention. The randomization assumption is also known as conditional exchangeability, which is that the counterfactual outcome is independent of specific treatment and the specific treatment received conditional on baseline covariates, aka that baseline covariates are sufficient to control for confounding. This holds if the measured baseline covariates block all backdoor paths in a directed acyclic diagram between A and Y. So here's a very simple directed acyclic diagram, or DAG, where GLP-1 causes the outcome of dementia, and baseline BMI is a classic confounder. We're both associated with initiating GLP-1 at baseline, as well as the outcome of dementia. And so if we say stratified our analysis on baseline BMI, or more commonly, adjusted for baseline BMI in the estimation phase of the analysis, we would meet this randomization assumption. We've controlled confounding and blocked all backdoor paths between A and Y. Now we're estimating the direct and total causal effect of GLP-1 on outcome dementia. And we're not just controlling for confounding here, but we're also making sure that when we're blocking paths, we're not blocking part of the causal effect of interest, or that by blocking a variable, we're not inducing an association by what's called conditioning on a collider, inducing an association that wasn't there before we adjusted for that covariate. So this is where DAGs can be really useful in formalizing our analysis and making sure we're meeting this randomization assumption. In this single time point intervention, meeting the randomization assumption is really straightforward. And we have a large set of potential baseline confounders that we might adjust for in our actual analysis of the Danish registry data, including demographic details, as well as medical history at baseline. But then in our ideal experiment, as discussed, we have a much more complex longitudinal structure. We're not just interested in a single baseline, single time point intervention. And this leads to a difficult challenge of post-baseline confounding. Here we have GLP-1 at baseline, which is affected by baseline BMI. But GLP-1 at baseline also affects future GLP-1 usage. That is also influenced by baseline BMI, as well as BMI after initiation of GLP-1 at baseline. And this longitudinal measures of BMI both affects continued use of GLP-1, as well as the outcome of dementia. And so how do we handle this complex longitudinal structure? Do we, as we did in a single time point intervention, is it enough to assure the randomization assumption to fit a regression or Cox model of the outcome on GLP-1 use, adjusting just for baseline BMI? No, because we are not accounting for the fact that those not on GLP-1 initially may experience more weight gain, which then affects the future switch to GLP-1. This is formalized in the DAG framework by an unblocked backdoor path. There's confounding by future BMI between GLP-1 use and the outcome dementia. So we're not actually estimating the single and direct effect of GLP-1 use on dementia, and our randomization assumption is not met to have a causal estimate of the parameters estimated from a regression or a Cox model. So alternatively, should we just then adjust for both baseline as well as follow-up measures of BMI? We're adjusting for all measured confounders. This must be enough to fully adjust for confounding and allow us to meet this randomization assumption and estimate the causal parameter of interest, right? No, here, by adjusting for follow-up measures of BMI, we're blocking or adjusting away part of the effect of interest. GLP-1 doesn't just directly affect the outcome dementia through future GLP-1 use and directly on the cumulative effect of baseline use, but also GLP-1 affects patients' BMI, which then in turn affects the outcome of dementia. So if we adjust for this follow-up measure of BMI, we're actually adjusting away part of the effect of interest. Our statistical estimates would be smaller than the causal effect, and we'll miss some of the interesting effect of GLP-1. So what do we do in this situation? Is this longitudinal structure not identifiable? Can we not meet this randomization assumption? We have to extend the randomization assumption to be what's called the sequential randomized assumption, or sequential exchangeability. This holds that Y A bar is independent of prior treatment, conditional on the observed past, aka for each intervention node, the measured past is sufficient to block all backdoor paths from that specific A at the specific time point T to future Y. And so we're not trying to make the randomization assumption hold for all intervention nodes at once, but each one sequentially. So for this first baseline GLP-1 use, the randomization assumption holds if we just adjust for baseline BMI. We're blocking any backdoor paths, and all effects of GLP-1 are on the causal pathway, either directly through future GLP-1 use or through mediated through effects on BMI, future BMI, not baseline BMI. And then we move on to making the randomization assumption holds for GLP-1 use at time 1. Here we adjust for baseline BMI, follow-up measures of BMI, but also past usage of GLP-1. And this allows us to block all backdoor paths. And so we're just estimating the effect of follow-up GLP-1 use on the dementia outcome. And so now that we know we have, if we can block backdoor paths sequentially for each A node, we're able to meet the sequential randomization assumption. We believe we're meeting these assumptions for identifiability, and we can move forward in the causal roadmap and consider what potentially time-varying confounders we may need to adjust for to meet the sequential randomization assumption. And this includes all medical history, medical purchases, ICD-10 codes, as well as hospital admissions, cardiovascular history, comorbidity and index, BMI, as mentioned, and renal disease, number of drugs prescribed, because physicians may not want to increase the drug burden on persons with early signs of dementia, as well as hemoglobin A1C, which is measured in only a subset of patients, as well as visit frequency. A second key assumption for identification is the positivity assumption. This positivity assumption is that there must be some positive probability of continuing to follow each regime of interest, i.e. the ideal protocol, at each time point, given that you have followed it so far and irrespective of the covariate history up to that point. So for example, if a patient's glucose control gets poor enough, treatment will essentially always be intensified. Therefore, it can't happen that there's a patient with poor glucose control who doesn't get intensified treatments. So an ideal experiment that enforces no intensification will not be supported. So if you remember back to earlier when we were setting up our ideal experiment, we allowed for intensification. That's because we wouldn't be able to meet this positivity assumption if we didn't allow for that in the ideal experiment, because it cannot happen that patients don't intensify, because in the real world, it will always happen if a patient's glucose control gets poor enough. There's also and so that's an example of violating the theoretical positivity assumption, but we also run into the practical positivity assumption. There must be support in the data to estimate the effects of complex combinations of covariates. So it may be that there's a theoretical longitudinal regime and set of observed longitudinal confounders, but if it's not at all in the actual data, it's just too sparse, we may not have adequate support in the data to accurately estimate our statistical estimate of interest. So we might, because we have, as mentioned, a lot of baseline and longitudinal confounders in many different time nodes, we want to balance making sure we meet the sequential randomization assumption by blocking all potential backdoor paths and controlling for baseline and time-dependent confounding. But we also want to make sure we're not violating this practical positivity assumption. So we might choose the covariates adaptively. And this is where outcome blind simulations can be incredibly important before finalizing an analysis plan and analyzing the real data. And we'll discuss that in a bit more in a little bit. And so we have these two assumptions, sequential randomization assumption and the positivity assumption, that sometimes can be at odds with each other if we have complex longitudinal data. And so, but if we meet both of these assumptions, we have we're saying that we can identify this causal parameter of interest, and we can translate this causal parameter of interest into a statistical target parameter. Here, the longitudinal G computation, we're expressing our causal parameter of interest as a formalized statistical target parameter. And I'll note that this parameter does not equal a coefficient in a single parametric regression model. This isn't an exponentiated coefficient from a Cox proportional hazard model. And because of the issues of time-dependent confounding, this cannot equal any point treatment parameter from any estimation method. And so we need specific estimators to solve this statistical problem at hand. And so that moves on from the causal model and identification step of the causal roadmap to estimation. Here we find a way to turn our statistical target parameter into a statistical estimate of interest that minimizes bias and has accurate inference. And so we need estimators that provide best statistical performance, minimizing bias, minimizing variance, leading to valid inference for the statistical estimation problem that we've already defined using the roadmap. We have complex longitudinal data as our observed data. We have the statistical model, the set of allowed distributions for this observed data, which remember, we want to be flexible, and because we don't have a strong a priori understanding of the set of allowed distributions, we want this to be a semi-parametric statistical model. And then we have our statistical target parameter, which is equal under the identification assumptions laid out to the causal parameter. And so this statistical estimation problem, the sum of the observed data, the statistical model, and the statistical target parameter, is an estimation challenge, especially because we have a high dimensional confounder set. We have extended follow-up, ideally using a fine time scale. We have a complex statistical parameter, the longitudinal G computation formula laid out. And we have a large statistical model because we have limited knowledge about the real world distributions of the observed data. If we use a narrowly defined statistical model, aka a parametric model-based adjustment strategies, that's going to lead to bias. And so this is where we advocate for using targeted machine learning estimation. This is a two-step process where we use super learning and ensemble, which is ensemble machine learning, where we use a weighted combination of different candidate algorithms, everything from linear regressions to machine learning algorithms. And this allows you to fit the data flexibly. And then we use targeted maximum likelihood estimation to target our estimates on the aspect of the data that we care about most. We update using the super learning fit to give the best estimate for this quantity. And we're not going to cover the details of super learning and TMLE in this talk because it's been covered in previous talks in this webinar. But if you haven't heard those or want a refresher, all of the previous recorded talks are on the webinar website for a deeper dive into targeted machine learning estimation. But targeted machine learning estimation is because it's so flexible, there's a lot of options that we need to decide before we actually analyze the data. And this is where simulations are important. Even if we're going to be analyzing real data, we use simulations to help inform the statistical approach. And at this point, I want to take a pause and invite Professor Mark van der Laan to say a few notes about simulation's role in the causal roadmap, because he's worked on this extensively.
All right.
Mark.
Can you hear me?
Yes, thank you.
Okay, good. Thanks a lot. Yeah, so after this long roadmap, and it's all about defining the statistical estimation problem for this problem. And the statistical estimation problem is defined by your knowledge about the experiment. And so we need to know a lot about the experiment. And that means in particular, you want to know your things like bounds and conditional independence assumptions, like for example, probability on developing dementia. Maybe it's supposed to be, it's always very small. Then that's something, that's knowledge you want to utilize. Similar for continuous outcomes, if there's certain bounds on them, you want to know that. Because, for example, part of the TMLE is the super learning, and the super learning is estimating stochastic relations, like how to predict the future from the past. And you want these predictions to respect the knowledge you have. So that's already where very detailed knowledge is important for development of the super learner in particular. Also, of course, we need to know the target estimate. And as Andrew discussed, that's not just a matter of the question of interest. It's also a matter that there needs to be support in the data for that. So that again requires a lot of knowledge about your data generating experiment. And in particular, in this case, knowledge about how the probability of being censored or dropping out depends on the past, but also the probability on the treatment, people staying on treatment given the past. And these things maybe can be learned from previous studies, but if not, then it would be very good to have at least outcome blind data so that you can see that. Now, once we have all that done, so that means we actually know our statistical model, we know our target estimate, then there is a very general approach, which is targeted maximum likelihood or targeted minimum loss estimation, which provides a template for construction of plug-in efficient substitution estimators. So what it does, it just estimates these conditional probabilities in your likelihood of how the future depends on the past. But beyond that, it also has to do in targeting step, and that's defined by the so-called canonical gradient of the target estimate. So that's something we can calculate mathematically. So in some sense, the TMLE is then defined. However, there are still many choices to be made. And these choices are, for example, what is your precise library of the superlearner? Which estimators are you going to include? Making sure at least they respect, the things we know to be true about the data chain distribution. And beyond that, there's also choices how to do the targeting step, because there are things, for example, if there's positivity type issues you want to be protected against, then there is this so-called collaborative target maximum likelihood estimation. There's also cross-validated TMLE, which makes the targeting step extra robust by doing the targeting on the left validation sample when the estimators, the superlearner is trained on the training sample. There is the choice of truncation, right? How do you truncate these treatment mechanisms and the censoring mechanism? What kind of truncation strategy are you going to use? And also in the TMLE update step, there are choices. And there is, in particular nowadays, quite recently, we developed higher order TMLE, which is able to further optimize the targeting, not just for the purpose of first order optimality, but also higher order optimality, so that your exact remainder gets optimal. So the whole point being that if you want to develop a statistical analysis plan, it's not a triviality like a Cox project has a model where you say, I'm going to include the following covariates. There are a lot of choices to be made. And even when, let's say, the statistical estimation problem has been around, and in the meantime, the R packages have been developed, these R packages will still have choices. And maybe we want to actually do some extra programming to bring in some extra things, extra advances. So how do you decide? No, we cannot just play and run the analysis with all kinds of choices till we see what we like, because that's precisely what we're fighting against. And so we need an a priori specified statistical analysis plan. So how do you do that? Now that's where simulations are a fundamental tool, which allows us to do that. So what that means is that we have to, on the computer, we have to specify these conditional distributions of the future given the past. Well, and how are you going to get these? That's potentially, if previous studies can be helpful there. Potentially you might get outcome blind data, so that at least you already have the conditional distribution of censoring and treatment, and you have your baseline covariates. But even then, there will still be choice to be made, but at least you know quite a bit about the bounds and on the random variables, so you can at least start choosing data chain distributions which respect what you know to be true. And then you can start simulating data, the same sample size, the same number of covariates as in your real study, the same types of covariates, and start evaluating different specifications of the TMLE, the library, all the things we talked about, and actually start evaluating across by taking like 1,000 simulated data sets of the same size and see how well you do with respect to coverage, confidence intervals, and also power and rejecting a null hypothesis and so on. And it's a great way to make sure the implementation is correct and there's no errors and everything is working as it should. And it allows you to kind of optimize the settings for the purpose of your study, which has very special characteristics, like maybe the outcome is rare. You don't want to use a crazy random forest. So all these things have to be carefully done. Now, this simulation allows us to do that. And then once we have run the simulation and made our specification, say this is good, then we have an a priori specified estimator, and then it's a matter of just submitting the code to run the data. And in this case, like I think with the Danish register, it's literally going to be like that. We don't have the data, we have to submit the code to the people who have access to the data. And so you can also imagine that even at the FDA level, this is could be happening, that we say, okay, you have to submit your statistical analysis plan, you have to give us the actual code you're going to run, and we'll run it for you. That's it. It's out of your hands. Now, this is precisely what is now also happening at the regulatory agency level. For example, there's the so-called Sentinel project. It involves an innovation center, which the main thing is the evaluation of targeted learning for the purpose of analyzing big observational real-world evidence type safety analysis. And this is a group of academics and FDA and industry evaluating on real data sets, precisely going through this whole roadmap of setting up a simulation based on outcome-blind data and making a choice of the specification of the TMLE and then actually running it on the data. We're also working on an FDA, another demonstration project led by Susan Gruber. It's working with the real world evidence group in the FDA. And there we also, we do up the same type of stuff. So setting up, but also starting to think about how to teach FDA reviewers how to evaluate a statistical analysis plan, because it has to come from both sides. There's how to design a statistical analysis plan, where you want to give all the power to that company or person, but you also want that the reviewers know how to evaluate it and know what to look for, what needs to be good and well done. And so, so a lot of action there, and I think a lot of the kind of reservations will eventually go away. But it is, of course, we are moving away from the kind of traditional world of Cox models with some covariates, where you didn't have to worry about that. This is now the reality. And but it's still a priori specified, and we should be doing this not just for an FDA approval. We should be doing this, and that's also what the real world evidence group realizes from the FDA. This has to be done for observational data analysis, and this is kind of what Andrew and his team is doing with respect to this Danish registry. So it's kind of a very interesting demonstration of this approach, which is really a way to do it. So I will leave it at that.
Thank you so much, Mark. On top of everything Mark said about the statistical reasons for conducting a simulation, I'll also add that there's some pragmatic reasons why we've done it in this specific project. It allows us to set up our code, make sure we know how to translate this causal roadmap into actual statistical computing language, and do things like benchmark how long these sometimes computationally expensive superlearner models take. And so this is ongoing work where we've actually created a realistic simulation of the Danish registry data. We did this based on sampling the coarsened multivariate distribution of both baseline confounders and longitudinal treatment regimes. And so far, we've implemented 3 estimators of statistical parameters as we defined using the roadmap. Under causal assumptions, this is equal to the difference in the simulated data between counterfactual dementia risk by 5 years under ideal protocols of continuous GLP-1 use versus an active comparator SGLT2 use. And this has allowed us to set up our code before analyzing the actual data, benchmark the statistical estimators we're using, decide on our superlearner library, as well as make sure we're not having convergence errors or our coding errors or unrealistic computing time, because as Mark said, to analyze the actual Danish registry data, we're going to visit Copenhagen in the fall. We have a time-limited time to actually analyze the data. So the estimators shown here using a single superlearner library include longitudinal G computation, as well as inverse probability of treatment weighted estimators, and longitudinal TMLE with a single superlearner specification. This is a work in progress where the next steps are going to be evaluating the estimator performance, like bias, variance, mean squared error, under different TMLE specifications, and which will allow us to then finalize our fully pre-specified analysis plan with all estimator decisions before we actually analyze the Danish registry data. So this simulation provides a wonderful trade-off between allowing flexibility in our estimation approach while being able to fully pre-specify our analysis before looking at the real data. So now I want to leave time for some questions at the end, so I'll move on to conclusions. This causal roadmap is leading to better causal, statistical, and scientific answers. we are clear on our causal question as well as its interpretation, and we are forced to be completely specific about what we want to know. We have a clear way to integrate contextual knowledge in defining the estimation problem. The scientific and subject area knowledge is not isolated from the statistical estimation approach. The statistical parameter is designed to come as close as possible to the motivating scientific question. We're able to still blind to the actual outcomes, choose estimators with optimal statistical properties, and verify their statistical performance to ensure valid inference through the simulation process. And I'd like to acknowledge the broader joint initiative for causal inference collaboration with our collaborators at University of California, Berkeley, Novo Nordisk, and the University of Copenhagen for all their work in developing this project and moving this project forward. And now we have time for questions in the last 12 minutes.
Great, thank you so much, Andrew. So any questions or comments from the audience? I had just a comment while people think about if they have questions. So I think we talked about, a couple different types of target causal parameters we could go after. So looking at, for example, the difference in counterfactual risk of dementia by some time point, or looking at whole counterfactual survival curves for one outcome or for more than one outcome, just to maybe add one more way of framing the target causal parameter to the mix, to tie things also back to Thomas's lovely talk, which is another thing we might be interested in doing is sort of quantifying so-called causal dose response curve. So how much does sort of incremental additions in cumulative time spent, for example, on GLP-1 translate to changes in risk of dementia? And so that's kind of a third category of target causal parameter we didn't talk about now, but I think will be really interesting in this analysis going forward, is using marginal structural models, which are really ways of defining target causal parameters. So I think they get mixed up sometimes with IPTW and estimators, but as a way of defining a causal parameter, how does that counterfactual risk change with, for example, each incremental month or 3 months or 6 months spent on GLP-1 versus an alternative second line regime. And so I think that's another area where it's going to be very interesting to build out this analysis plan. Oh, I see we have a question.
We have a great question from Christian Torp Peterson. Real life data are always full of surprises. What do you do if one of your simulations overlooked one of these uncomfortable surprises? That's a great question. And that's one of the reasons why we're trying to construct our simulations from a realistic data distribution from the Danish registry data while still being outcome blind. If we constructed the simulation fully artificially, I would say maybe include as a confounder alcohol use, but that's not actually something we can get from the Danish registry data. So we have to deal with the potential unmeasured confounding there. But as you mentioned, simulations are never going to fully capture what's in the real life data. I don't know if Mark or Maya have any additional comments, but the statistical analysis plan you build out of your simulation shows how much work you put into defining the causal roadmap and setting up the simulation. And then if you run into one of these unfortunate surprises in the real life data, you can update the statistical analysis plan with how you address that challenge, but you've been honest about everything you were able to plan out before you ran into that uncomfortable surprise and why you had to make a change to the analysis plan afterwards. But that's just been in my analytic experience.
Yeah, this is Mark. So yeah, that's a good question, but that's also precisely why we do these simulations, is to be prepared for the typical surprises you would encounter if you would just start playing with the data. And so by setting up a simulation and really getting all the knowledge you can think of and have, and best scenario is that we get outcome blind data, right? Because then we have actually all kinds of important information. So there's no reason why we cannot do a realistic simulation. It doesn't have to be the same data distribution. It's all about making sure, that we know enough about the data distribution that we can set our specifications in a reasonable way. Yeah, if somehow the moment we run the code, in spite of the simulations respecting all we knew and maybe already based on outcome blind data, if somehow in the code there was an error, in the, not so much in the code because there wouldn't be an error anymore, but in the outcome data, let's say, there were errors. Yeah, that's something we cannot protect against. And if we find that out later, yeah, clearly we have to redo it. But that's a matter of that the data quality has to be reasonable. And yeah, and that needs to maybe done by somebody else, right? Who needs to make sure that the data provided is truly what it's supposed to be, and there are no errors somehow crept in.
We have another great question from Lars. Oh, sorry, Mike, do you want to say something else?
Oh no, I was gonna. Yeah, thanks for that, Mark. Can I take the question from Lars, Andrew?
Yes.
Near and dear to my heart. So Lars Kosham asks about the positivity assumption. What if a treatment is contraindicated in a subject? So say they're allergic to GLP-1. Do we take it into account? And supposedly, or in theory, you'd have to exclude them, but how do you do it? So I think there's three levels of answer to that question. The first is exactly in terms of defining the target population. So if there are persons in the data set who, based on their baseline characteristics, are just never going to be, based on their measured baseline characteristics, are never going to be eligible for, say, GLP-1 or the active comparator, then that's indeed something you can do in defining your target population, which makes sense too in terms of interpretation. What's the effect of GLP-1 in a population that actually is eligible to get it? The second two levels of this, though, are what if someone develops a contraindication or a side effect that then means they would always switch off of the drug or discontinue it. And so if that's a measured covariate, it's a side effect that we measure and we think actually also may be important for the outcome, then that's a great example of where you really don't want to exclude patients based on post-baseline or post-baseline variables that in fact may have been affected by the treatment they received earlier, that we're back into this conditioning on a post-baseline variable in that case. And so a powerful approach to that source of positivity violation that occurs as a result of a time varying characteristic is to define a dynamic regime. And so we didn't have time to get into that too much, but basically you extend those ideal protocols to be ideal protocols that you would actually do in practice. You say, okay, go on GLP-1, stay on it with no more than 9-month interruptions, unless you develop an absolute contraindication, in which case you're allowed to go off of it. And that then becomes the ideal protocol you're contrasting. And then the kind of third level, which is what if there are things that you haven't measured about people that make them say ineligible, essentially cause these positivity violations. And for that, they don't actually cause a positivity violation in the sense they are not measured and they're not something we can adjust for in any case. So in that sense, they don't undermine our support and our observed data. But factors like that, if we think they're also important for the outcome, could be important sources of unmeasured confounding that, again, we have to take into account both in our interpretation and then potentially in sensitivity analysis. I don't know, you want to add anything to that, Mark? That was a long-winded answer, but it is a deep and important question.
Yeah, and I think this also beautifully demonstrates how this whole approach we're talking about applying the roadmap dives into truly understanding everything about your experiment. So contrast that with running a Cox-Purser hazard model, where you don't even have to talk to anybody and you can run it. This is requiring precise understanding of what kind of biomarkers do we have, how do doctors treat, are there situations where they're forced to make a choice instead of having still the ability to experiment between different drugs. And all that is absolutely crucial to define the questions of interest, in this case, the treatment regimens of interest. And so, yeah, the way Maya said it was right on.
Great. So we are just about at the top of the hour. I want to thank all of our fantastic speakers for a series of really thought-provoking and nice talks. And thank you to the audience. So this is the last scheduled webinar for right now. We're going to take a little bit of a spring break, or summer break rather, but please stay tuned and we will be scheduling future webinars and other events coming up. So thank you all again and enjoy your morning or evening. Andrew, you look like you want to make an announcement though.
Oh, I was just going to say, if any follow-up questions spring into your mind over the rest of today or the next couple of days, feel free to post any follow-up questions on the webinar website. We'll also be posting recordings of the talk there, and we'll get notifications and can answer it through the website itself. And that's also what we will make announcements about upcoming webinars after our summer break.
Wonderful. Thank you all very much. And we'll see you soon.
Thank you again, Thomas. We just lost Lars.